When considering moving objects, including when using Newton's laws of motion, there are some things which are worth stating clearly because we will use them throughout. First off is the difference between speed and velocity. Speed is a measure of how fast something is moving, but it does not tell us the direction of motion, whereas velocity tells us how fast something is moving and in which direction. So speed only has a magnitude, but velocity has both a magnitude and a direction. Velocity is known as a vector quantity, and when we write vectors, we usually denote them with a little arrow on top of the character. Another example of a vector is acceleration. Speed, being just the magnitude of the velocity, is called a scalar quantity, and it can just be written without any special notation. If something is moving at 10 meters a second and travelling north, then its speed is 10 meters a second, but its velocity is 10 meters a second northwards. It is possible, of course, that the speed can remain the same, but the direction changes. So something moving at 10 meters a second southwestwards still has a speed of 10 meters a second, but its velocity is now 10 meters a second southwest. We will see a real example of this in another video on orbital motion when we consider how a satellite orbits the Earth. Sometimes, for simplicity, we can interchangeably use speed and velocity as long as it does not confuse the argument. But strictly speaking, we should take care because it can be important. At times I may omit the arrow from vectors just to keep things simple, but hopefully the meaning will still remain clear. So velocity is a vector, speed is a scalar quantity, and we may sometimes use them interchangeably. Now let us define how displacement, velocity and acceleration are related to each other, and to help us do this we will draw some simple graphs of each of these quantities against time. The displacement of an object is just the difference between its positions over a certain interval of time, and we can plot the position versus time in a graph like this. Imagine we are at a certain point at a certain time t1. Then at a later time t2 we are at another position. Now if the position at time t2 is equal to the position at time t1, then we have not moved position at all. That is, we are at rest. Over the time interval t2 minus t1, we have not moved any distance, so our displacement is 0. If x2 is different to x1, however, then we have a displacement and it will equal x2 minus x1. And we have taken a time of t2 minus t1 to make the move. If we plot position versus time, then we can keep track of where we are, and a plot like this tells us how the position of an object is changing with time. Position and displacement are measured in units of meters as a standard. This is an international system of units known as SI units. But of course we can use whatever convenient units we like, hence sometimes we use kilometers, sometimes miles, sometimes inches. Sometimes for very large distances we can even use the distance of the Earth from the Sun as a unit, which is known as an astronomical unit. In a similar vein to velocity and speed, displacement is a vector, whereas distance is a scalar quantity. Generally, this distinction does not really cause problems because usually velocity and acceleration, being vectors, allow us to work out which direction something is moving, so we can be a bit more loose with using position, distance and displacement, but it is still worth noting that displacement is a vector. So let's take a new plot of position with time, and what this graph shows is initially a rapid change in position with time, then some time spent at rest where the position is not changing, and finally a linear change of position with time. Having got an idea of how position is changing with time, we can now define what velocity and acceleration mean. We know the units of velocity are distance divided by time. So for example, we say meters per second or miles per hour. So velocity is the rate of change in displacement or position with respect to time. How far we have moved and in what time. Strictly speaking, the instantaneous velocity v of an object at a certain time is derived by differentiating the displacement vector with respect to time. And we write this as v equals dx dt. We can apply Newton's calculus to do the differentiation like this, but we do not need to go into that here just to keep things simple. So when we do the differentiation of our three types of motion, we get velocity plots like this, where we initially have an increasing velocity, then we have zero velocity when the object is at rest, and finally we have constant velocity when the displacement is changing linearly. Acceleration is the rate of change in velocity with respect to time. We say this as a equals dv by dt. And the units of acceleration are velocity divided by time, so for example, meters per second, which we usually just say as meters per second squared. We have differentiated displacement to get velocity, and now we differentiate velocity to get acceleration, and we get a plot like this. So when the velocity v is increasing, then the acceleration is constant. But when the velocity is either zero or the velocity is constant, then the rate of change of velocity is zero, and hence acceleration is also zero. So to summarize, if we know how an object is moving, changing its position with time, then we can work out its velocity and acceleration, and these relationships between displacement, velocity, and acceleration are as shown. There is one other feature of position which is worth noting, and that is the fact that it's important to know the displacement, how much a body has moved, rather than the absolute positions of the start and end points. This is saying that there are no special positions in the universe, and mechanics of how things move are only reliant on displacement and therefore velocity and acceleration. Imagine a position and time plot like this when the body moves from position x1 to x2. In this motion, let us take the displacement as dx. If we start somewhere else, for example at x equals 0, and still have a displacement dx, then we can see that the slope of the graph is still the same and dx and dt are still the same. We know that velocity is dx by dt, so in both cases we can get the same result for velocity no matter where we start our motion. Similarly, we can start our motion at any time t as long as our time interval dt is the same, and if that's the case then our velocity dx dt will still stay the same. This is an important property of Newton's universe. It does not matter about the absolute position and time that a move starts. It only matters how far the body moves and in what interval of time. This means that no matter where we are and what time, we can call the position and time the origin, x equals 0, t equals 0. And being able to do so greatly simplifies how we deal with the motions of bodies. So in those cases where we are considering motion, like throwing a ball in the air, we will simply just assume that the starting point is x equals 0 and the starting time is t equals 0. In Newton's world, we only really need to know a small number of key things about an object: its mass, how it moves, and any forces acting on it. And if we know these things, then we are able to work out what will happen to that object in the future or what happened to it in the past. This is why Newton's theories are so powerful, because they help us to describe not only how things are moving now, but how they will move in the future. Which is why we can predict things like solar eclipses and when Halley's Comet will next return. We will see how to work out some of these things in other videos. I hope you found this video interesting. Until next time, keep thinking physics.